Welcome to the second talk of the Fall 2018 seminar series on modern artificial intelligence at the NYU Tandon School of Engineering. This series aims to bring together faculty, students, and researchers from New York and New Jersey to discuss the most important research trends in the world of AI. The talks are live streamed and watched around the entire world in Abu Dhabi, Shanghai, India, and Europe. The speakers are all renowned experts whose research is making an immense impact on the development of new machine learning techniques and technologies and helping to build a better, smarter, more connected world. I'd like to thank Dean Jelena Kovacevic, as well as my own Department of Electrical and Computer Engineering for hosting this series. I extend special thanks to Chair Ivan Selesnik for his support, and Raquel Thompson, Caitlin Hamilton, and the media team for being a very capable team and for the tremendous work they have done. The overall mission of NYU Tandon is to promote technologies that can be used for the benefit of society. And I'm happy to have the school's wholehearted support for this seminar, which explores the many ways in which AI is benefiting the world. Without further ado, let me introduce our esteemed speaker and tell you a little bit about him. David Blei is a professor of statistics and computer science at Columbia University and a member of the Columbia Data Science Institute. His research is in statistical machine learning, involving probabilistic topic modeling, scalable Bayesian algorithms, and interpretable generative models. He works in a variety of sciences, and he works on a variety of applications using data from text, images, medicine, the social sciences, and the natural sciences. David has received several awards for his research, including a Sloan Fellowship in 2010, Office of Naval Research Young Investigator Award in 2011, Presidential Early Career Award for Scientists and Engineers in 2011, Blavatnik Faculty Award in 2013, ACM Infosys Foundation Award in 2013, and a Guggenheim Fellowship in 2017. He is the co-editor-in-chief of the Journal of Machine Learning Research. He's also a fellow of the ASCM and the IMS. David will speak about the blessings of multiple causes. Please join me in welcoming him now.
Thanks, Anna. Thanks. Can you hear me? Make sure I remember to turn this on. Yep. Thanks for inviting me to this great series. My name is Dave Blei from Columbia. I'm going to talk about the blessings of multiple causes. So before I start talking about the blessings of multiple causes, I wanted to tell you a little bit just about the general area in machine learning that I work on in my group and with my colleagues. So it kind of goes without saying these days that we have complicated data and we want to make sense of it. Okay, this used to be something I had to assert, but now it's something that's kind of intuitively obvious to everyone who takes a look at those two sentences. We can have data from large-scale scientific instruments, build big telescopes that collect terabytes of physics data, and the physicists want to make sense of it. Maybe we build Facebook, and then all of a sudden billions of people are communicating with each other and connecting with each other in a big online community, and that produces data that we want to make sense of. Maybe we're an economist, and we're looking at people who are shopping at the store, and we have millions of customers shopping at the store and filling their baskets and checking out, and we want to make sense of that data, understand something about how people buy items. Or maybe we are analyzing text. We have a big collection of online or electronic texts, and we want to understand what's in them and want to be able to navigate them and search them. So I want to unpack these two phrases a little bit first. What does it mean to have complicated data, and what does it mean to want to make sense of data? Well, complicated data can mean a lot of things. You know, most immediately when I think of complicated data, I think, oh, it's a large data set. There's many, many data points, and it has many dimensions, right? I get, like I said, terabytes of data from the physics telescopes, and each data point has many, many types of measurements in it. But data can be complicated for other reasons too. Might be unstructured, right? So your grandparents' data sets were matrices, but data now can be a big bag of unstructured things like text, where it's not necessarily easily formed as rows and columns, but it's a collection of words in a sequence. It has syntax and semantics and other linguistic attributes like that. And data can also be complicated because it's multimodal and interconnected. So again, the social network can't be seen easily as a matrix. It's really a graph of data points, people who are interacting with each other, communicating with each other, and maybe clicking on articles and links and and reading each other's messages and so on. And so this is complicated in other ways. It's complicated because it's this big interconnected jumble of many different types of data points. So that's why these are some of the ways that data is complicated. Whoops. Oh, I don't know how to go back. Oh, did it go back? Okay. Everything's good. Feel free to interrupt me with questions while I fumble, especially. So what does it mean to make sense of data? Data is complicated in lots of ways. What does it mean to have to make sense of data? Well, that also can mean many things. I want to unpack that a little bit. When we think of making sense of data, the first thing we think of is we want to make predictions about the future, meaning I ingest a bunch of data, and I want to know what my next data points are going to look like. Okay, and so most machine learning algorithms are based on this idea, right? Deep learning is about ingesting a bunch of data and then predicting what the next data is going to look like. But there might be other ways that we want to make sense of data. One is we might want to identify interpretable patterns in the data. Okay, so I'm a sociologist and I have Facebook on my computer and I want to find communities and understand how society unfolds. All right, and I want to be able to form a real theory and understand it, and I need interpretable patterns to be able to do that. Merely being able to predict what's going to happen next on Facebook is different from being able to find a pattern that I can interpret and that gives me insight into how the data works. And most ambitiously, we might want to do real science, confirm, elaborate, and form causal theories. I want to understand how the universe works from the data, not just predict what the telescope's going to tell me next. And I want to understand how the universe works in a robust way. I want to understand a real theory that can be confirmed. So this is what I think of as making sense of data. So the field I work in is probabilistic machine learning, and it's about developing machine learning methods that connect our domain knowledge, for example, about society or about physics, to the data that we're trying to analyze from that domain. Probabilistic machine learning helps us blend these assumptions and the data to learn about the world. And our goal in this research field is to build probabilistic machine learning that is expressive, scalable, and easy to develop. Okay, by expressive, I mean that a physicist can walk into my office and tell me about the latest developments in physics theories, and we can turn them into a machine learning algorithm that respects those theories. Scalable means we can then handle the terabytes of data that's coming from the telescopes. I don't even know if these telescopes are real. It's just the example I use when I look at this picture, just so you know. And easy to develop, which means that we want to be able to do this quickly. I want to be able to transform her theories about the universe and this massive terabytes of physics data into a method that ingests the data, respects her theories, and then gives me interpretable patterns about the universe or causal inferences about the universe. This is our goal. Oops. Okay, so some examples of some of the work we've done. So in my lab, we've done a lot of work on finding interpretable patterns in big data sets. So for example, we have a method that can find communities, overlapping communities in big social networks. Here's a picture of that. We look at fMRI data, so we can work with a neuroscientist and ingest lots of fMRI measurements and then find interpretable patterns of what areas of the brain are activated when the subjects are looking at different things. We do a lot of work on what's called topic modeling, which is about finding interpretable patterns in text data. So here we ingest 2 million, 1.8 million articles from the New York Times, and we learn these groups of words that are somehow thematically related, like stock, percent, companies, fund, market, bank, investors, and so on, automatically. In comes text without any labels, out comes these interpretable patterns about what kinds of themes pervade those texts. We've looked at genetic data. This is a population genetics analysis of many, many people's genotypes. And lately, we've been working with an economist to look at consumer behavior data. This is a complex econometric model that we fit to millions of customers shopping for groceries. And the economist was excited because it showed us that crackers and cheese go together. That's what this picture tells you. And that's a big result in econometrics. Okay, so these are the kinds of things we work on. And each of these projects, each of these machine learning methods goes through what retrospectively we call the probabilistic pipeline. which says that we start with our knowledge of the world and some question we want to answer about the world, and we use it to make assumptions. Okay, this is a graphical model. Some of you might be familiar with it. It's basically a way to represent graphically hidden patterns in the world and observed data. Shaded nodes are observed, unshaded nodes are hidden. So we translate the physicists' assumptions and theories into a graphical model. It's a formal mathematical object. Then we take our big data set and our model, and we square them together to uncover the patterns that live in the world. And what this means is I want to fill in these hidden variables given the observations. And then I take those discovered patterns and we use them to do stuff. Call the physicists back and say, hey, what did we learn about the universe from these discovered patterns? And I like this picture. It seems a little vacuous, but I like it because it separates these key activities of making assumptions, doing computation with those assumptions and data, and then using the results of that computation to do things. And it makes it easy to collaborate, not easy, it makes it easier to collaborate with domain experts on statistics and machine learning problems. I'm having a hard time with the clicker. Now, it's a pipeline, but as I mentioned, we want to make probabilistic machine learning easy to develop. Our vision is that this will eventually be a cycle, a loop, where we make assumptions, uncover patterns, you do something with those patterns, and then go back and say, hey, what went right, what went wrong in that model, and revise our model. Right? I want to do this with The Economist. Go through, say, hey, what makes sense, what doesn't make sense about our model of people shopping, and then revise our model based on that. Again, if you're interested in reading about this way of thinking about domain-specific machine learning methods, you can look at some of these papers. So what I want to talk about today is causal inference. How do I use all that stuff that I just showed you about to really understand the world through observational data? And this is important in every field: genetics, economics, physics, medicine, sociology, etc. Every field right now has accidentally found a lot of data, like a bunch of people talking to each other on the internet, and has the sense that they can use that data to understand the world through the lens that they care about. And I want to show you how to use probabilistic machine learning to do causal inference. Okay, I want to emphasize this is joint work with my brilliant student Yixin Wang. Anything you like about this work is Yixin. What you don't like about it is me. Okay, so we'll start with an introduction to this idea, the blessings of multiple causes, which is an algorithm we call the deconfounder. Okay, so forget about neuroscience and physics and all that good stuff. Let's talk about a very frivolous causal inference problem. You're a big-time movie producer, and you have a data set of who's in a movie and how much money that movie made. And what you want to do is understand the causal effect of putting an actor in a movie. Okay? If I'm going to make a movie and I'm going to put Keanu Reeves in the movie, how much more or less money will the movie make because I cast Keanu Reeves? Okay, that's the problem you want to solve. I want to be clear. We're using this problem just to illustrate the method. Okay, so I'm going to analyze data like this, but I don't know much about real movie producing. Okay. Now, this is a causal question because it's a question about an intervention. What will the revenue be if I make a movie with a particular cast? Okay, when you have a prediction you want to make under an intervention, that's a causal prediction. So, here's our data, and this is real data. We have the cast of the movies. You see, like, Avengers: Age of Ultron. Here's Robert Downey Jr. is in that movie, and it made, whatever, $1,274,000,000. Okay, and we have a big data set like this. Who's in the movie, how much money the movie made. So, naively, what would you do? Well, you'd fit a regression from who's in the movie to the revenue, right? You would just fit whatever, linear regression from binary variables that encode who's in what movie and a response variable that's how much money that movie made. And this, or you'd learn a deep learning model, same thing. This estimates how much revenue changes when an actor is included. Okay, right? If I throw an actor into the movie, if an actor appears in a movie next year, this helps me estimate how much money that movie is going to make, or make more or less if that actor happens to appear in the movie. But the first point I want to make to you today is that this is not necessarily a causal inference. Okay, regression is not a causal inference because whether an actor appears in a movie is different from whether you put an actor in a movie. Okay, it sounds subtle, But this is a key difference between making a prediction under an intervention and making a passive prediction. That just says the world's going to keep going the way it's going, and this is how I can predict what's going to happen. Okay, and this should be clear to you from this photograph. Have any of you seen this movie? This is typical now. Okay, this is From Russia with Love. It's a James Bond movie from 1963, I think. And have any of you seen a James Bond movie? Okay, good. So you know about James Bond. So let's see if this works. Okay, so this is Sean Connery. He's James Bond. He's a secret agent, all right, in England. And this is Q. He's the guy that gives James Bond all the cool gadgets that he uses, right? So he always has like cars that shoot guns and oil slick and stuff like that. And Q is the guy who makes all that stuff. And this is M. M is in charge of the whole operation. M is the head of the Secret Service in England in the 60s, in the James Bond movies. Now, here's what you need to know. James Bond movies are all hits, okay? They make a lot of money. And also, James Bond is a series. So every James Bond movie has James Bond, Q, M, and other people like Miss Moneypenny. Okay? So what's the problem with regression? Well, oh, there's another thing I need to tell you. This is just the rest of the talk, is going to be this picture. And the other thing I need to tell you is that M and Q, they appear in every James Bond movie. You can't have a James Bond movie without M and Q in it. So what's going to happen if you run that regression, or if you fit a deep learning model from cast to movie revenue? Well, it's going to learn that M and Q are worth a lot of money. They only appear in James Bond movies, and James Bond movies are all hits. So then when you're making your movie, you're going to say, hey, I can get M for cheap. So I'm going to get M and put M in my movie. It's definitely going to be a hit, but it's not. M is only in this movie because it's a James Bond movie. And, well, I don't know, maybe M's a really good actor. But the point is that it's Sean Connery who's driving the success of these movies. But the regression cannot see that. So what is the problem? What is the James Bond movie issue? The issue is an unobserved confounder. Okay? A confounder is a variable that's not in your data. Notice there's no variable here that says, is this a James Bond movie? And it affects both the causes, in this case the cast, who's in the movie, and the effect, in this case the revenue. Okay? And so James Bondness is one possible confounder. When I'm going to sit down and make a James Bond movie, first of all, I get Sean Connery, and then I call up M and Q and Miss Moneypenny, and I say, hey, I'm making another movie, you know, come into the movie. And of course, whether or not it's a James Bond movie also correlates to the effect, because it means that it's going to be a hit. Okay, and there's lots of confounders in this data. An action movie, you're gonna put action stars in the action movie, and action movies might make more money than, say, independent movies. Okay, the point is, the confounders are going to bias the regression coefficients. If you run a regression from actors to revenue, some actors are going to be overestimated, like M and Q, and some actors are going to be underestimated as a consequence, like Sean Connery. All right, so the difference with causal prediction is that it involves an intervention. What would happen if I put Oprah Winfrey in Star Wars? Those are the kinds of predictions we're trying to make in this example. If you're familiar with causal inference, then I don't want to get too into this. You know that there's like a big war between the wizards of causal inference, Rubin and Pearl, and they have different notation. All wars in academia involve notation. And so we're going to estimate this. In Rubin's notation, we're going to estimate the expectation of how much money the movie makes with a particular cast. And in Pearl's notation, we're going to estimate the expectation of how much money the movie makes, given that I intervene on the particular cast. Okay? If you're not hip to causal inference yet, don't worry about that. Okay, so how do we do causal inference? We're a big-time movie producer. We got this data, but we realized when we looked at that James Bond picture that there's an issue. Here is the classical solution to causal inference. I've got my data of actors and revenue, and what do? I first think about all the confounders that might be in the data that I haven't thought of. Then I hope that I can measure them, and I measure them. I add them to my data, and then I estimate the causal effects from the data that includes my original data and the confounders that I measured. Now, what's the problem with this? This approach requires that we measure all confounders. Okay, I need everything that could be confounding my estimates to be measured. Famously, the books and theories and papers about causal inference say that if you have, whether or not you have measured all the confounders is untestable. Right? There's no way from the data alone I can determine whether or not I have estimated all my confounders, measured all my confounders. And so the classical solution to causal inference is one that rests on hope and worry. Right? And that's why I drew this scientist with worry eyebrows. So that's the issue. But this problem of figuring out how much money actors are worth is not a classical causal inference problem. Classical causal inference would be like, you know, we all have headaches and some of us take Advil and some of us don't, and we see whose headaches went away. And the issue with the confounder there is that if Advil doesn't work for me, I'm not going to take Advil. I'm going to take something else, and same with you. And so then we're going to get an overestimation of how well Advil works because only the people for whom Advil works will take Advil. Right? That's the classical confounder in a classical causal inference. But there's only one cause there, whether or not you take Advil. Here we have many causes, one per actor. And so this is a multiple causal inference problem. Okay? It's a problem where I have many possible causes and an effect. And the point of this work is that the multiplicity of actors can help us sidestep some of the strong assumptions that we make in classical causal inference. And I'm going to show you how. Okay, that in particular, the multiplicity of actors can help us, can give us indirect evidence for some of the confounders that are lurking in this data set. Okay, and so here's our procedure called the deconfounder. We have our data, actors and revenue. And what we do at a high level is first we take just the actors, who's in what movie, and we model the actors with a probability model, the kind of model I showed you in the beginning of the talk. Okay? Then we take that model. If you're familiar with it, so you might take your actors and fit a matrix, a probabilistic matrix factorization to who's in the movie. Then you take your model, and you take each movie and you estimate the local latent variable, the per movie latent variable for each movie, and you use that as a substitute for the confounder. Okay? At a high level, do a bunch of machine learning on the actors to estimate a per movie variable, and then use that per movie variable in a model of the actors and the revenue to correct for the confounders. I'll go into more detail later. But that's the idea. What's nice is that in this first step, we can check this model. Okay? And we can check whether or not we have done a good job of modeling who's in the movie, and that tells us whether or not we've done a good job of modeling the unobserved confounders. Again, if you're familiar, concretely, you could fit and check a probabilistic matrix factorization of movie casts. You could then infer the per movie variables in that matrix factorization, and then correct for the confounder with a regression from casts to earnings that also includes these per movie variables. That's the idea operationally. Fit matrix factorization, infer per movie variables, take those per movie variables and your original casts and fit a model of the outcome, and that is a causal model, up to some assumptions that I'll talk about. All right, what's good about this? It's a checkable approach to multiple causal inference. It blends unsupervised learning, model checking, and causality. And as I said, it requires weaker assumptions than classical causal inference. There are assumptions. And it works. So we did it with that data, and as you would hope, Q and M go down and Sean Connery goes up. Okay, so now we're going to open a movie producing studio. So that's a silly problem, figuring out how much money actors are worth, but multiple causal inference comes up in lots of important problems too. So for example, one important problem in genomics is how do genes affect a trait? All right, some of us have the ability to fly, some of us don't. Which gene is it that's helping us fly? And in this kind of problem, the causes are the genes. So we all have a bunch of genes, or SNPs, single nucleotide polymorphisms. And the effect is the trait or the phenotype. And the confounder is that each person's ancestry induces correlation among the genes. Okay? My family's from Hungary, and so there's some genes that are active because of my Hungarian background. And and if you ran a regression, that's like some of those genes are like M, and some of those genes are the ones that are giving me the ability to fly. And so you would misunderstand the Hungarian genes as giving me the ability to fly if I ran a regression. Same with M and Q. Okay, and so this is a real-world problem that one could use this method for. All right, another problem is how do sports players affect how well the team is doing? I'm a little bit out of my league with sports, but here the causes are who is in the game, which players are in the game. The effect is how many points the players score in the game. Let's say it's UConn basketball. And the confounder is that the coach uses multiple players together. Okay, Anna and I might be on the same team, and the coach puts us in together because we play well together, but really Anna's driving the points, and I'm just always there when she's in there. And so then a regression would misunderstand that I'm a worthwhile basketball player when really it's Anna. All right, and in economics, how much do the prices of items affect how much money is spent? Now again, the causes are the prices of items for sale. So I have lots of items for sale in the store. People are buying it. The effect is how much money is spent. We want to know how much money are we going to make in our store. But the confounder are holidays. Okay, so like tomorrow's Halloween. Is tomorrow Halloween? Thank you. Wednesday's Halloween. That affects the prices and demand of multiple items. Okay, it's not that people are willing to buy more, spend more on candy. It's that Halloween raises the price of candy and people then buy it. What's important is that it's not that there's one type of Halloween candy. Thankfully, there's many types. And so it affects the prices of multiple items, all the different types of candy. All right, so again, the idea is to find, fit, and check a factor model of the assigned causes, use it to form substitute confounders, and then use the substitute confounders in a causal model of the outcome. So I promised to tell you the assumptions. The main assumption is that there is no unobserved single cause confounder. Okay, so this paper is called The Blessings of Multiple Causes. If there's a confounder that only affects whether Sean Connery's in the movie and the revenue of the movie, the deconfounder cannot help. All right, because the deconfounder uses the correlations between cast members as evidence for what we call multi-cause confounders. I'll define it formally in a bit. Okay, the point is, however, this assumption is weaker than the classical assumption that says that you need to know what all of your confounders are. Okay, and the argument, it's a little loose, is that in domains where you can observe many, many, many causes, the chances of a single cause confounder goes down. But of course, that's a domain-specific matter. There's other assumptions too. If you're interested, I can explain them later. Okay, so here are our results. So we took the data set I showed you of movies and how much money they made. We fit the naive regression that the silly movie producer uses, and then we fit a factor model, estimated substitute confounders, and fit a more sophisticated regression that the smart movie producer would use. And what we learn is this. Okay, so let me see if I can remember their names. So first of all, some actors are overestimated. What does that mean? That means that they're actually not as good as they seem. That when you account for these confounders like genre of the movie and so on. And so Arnold Schwarzenegger and Robert De Niro and Brad Pitt, for example, are overestimated actors. Again, I'm not, this is just sanity check. This is the digits data set of movie producing. Now, underestimated actors, I don't know why they're underestimated. These are actors whose values go up. And so Antonio Banderas, Cate Blanchett, Nick Cage, is that right? And Owen Wilson are somehow underestimated. And it's weird, again, I'm reading the tea leaves here a little bit, but it's sort of believable in that Owen Wilson might appear in comedies and things like that tend not to make as much money, but when he's in the movie, it does better, and so he's an underestimated actor. And then the most corrected actors, these are the actors that move the most one way or another, and they include actors that are in lots of smaller movies. Willem Dafoe came up. My wife has a crush on Willem Dafoe, so I was happy and sad to have to include his picture in the talk. What do you mean by most corrected? these are some examples of actors that go up. These are examples of actors that go down. These are actors whose regression coefficients change the most. These are the ones that were most corrected by going from non-causal to causal. Just ways of us understanding what the model is doing and what the difference is between the two fits. Okay, so that's the basic idea. Fit an unsupervised machine learning method to the assigned causes, use it to form an estimate of the substitute confounder, use the substitute confounder in a downstream prediction mechanism, and that's a causal inference. So I want to give a few more mathematical details about this and also tell you a little bit about why it works. Okay. So notation, call AI, vector AI, the observed assigned causes. Okay, so there's M actors in Hollywood, and I is the index of the movie. This is a bunch of binary variables. It's 1 if the actor's in the movie, and it's 0 otherwise. We're going to use Rubin's notation here, and the potential outcome function is yi of a. All right, and just to, if you're not familiar, to teach you a little bit about Rubin's notation for causal inference, this is a function. It's a function for each movie. So I might be Star Wars, and the function takes in a cast and spits out how much money Star Wars would have made if it had that cast. All right? Set aside the ridiculousness of it. It is ridiculous. But the point is, it's a function. Takes in cast, spits out how much money Star Wars would have made if it had that cast. The observed outcome is, of course, yi of AI. How much money Star Wars made with its cast, the cast of Star Wars. Okay, but the whole idea behind Rubin's causal framework, which is really equivalent to Pearl's, is that I don't want to get into that, but the whole idea about Rubin's causal framework is that you only observe this, but somehow this is underneath everything and you're interested in this for other A's. I want to know if I change the cast of Star Wars, how much would it have made? So our observed data set is A1, the first movie, and how much it made, all the way up to the nth movie and how much it made. And our goal is to calculate something about the counterfactual outcomes. For example, I might want the expectation under the population of movies of how much money a movie will make if it has a particular cast. Okay, let's put Oprah Winfrey and Keanu Reeves and Christopher Walken and Willem Dafoe and Cate Blanchett in a movie. And on average, how much will that movie make? So we estimate that with Monte Carlo here. However, notice that it's not yi of AI, it's yi of a. Right? It's yi of this made-up cast that I'm interested in. Question?
Is there some normalization for cast size?
For what?
For the size of the cast?
No, we're not. So we're saying that there's just this function, it takes in a cast and spits out. So no, we didn't normalize for that. The problem with this is that we only observe yi of AI, and that is called the fundamental problem of causal inference, that we only get to observe one outcome per unit. And the deal is that this is what we're interested in, this expectation. This is an expectation that we can calculate from our data, right? We can approximate this expectation, yi of AI, given that AI equals A. We can calculate this. Also set aside the ridiculousness of we can't calculate it for real because we won't have the support in our data set, but in theory we could. But these are not equal. Okay? When there's confounders that are unobserved, these are not equal, and that's the core issue. Okay, so what is the classical solution? Again, the classical solution is to measure all the confounders that you might care about. W1 to Wn, is it a James Bond movie? Is it an action movie? Is it a comedy? Is it a superhero movie? And et cetera. These all might be confounders that affect the cast and affect the revenue. And what you hope, is that they satisfy what's called strong ignorability. That's an independence assumption that says that who's in the movie is independent of how much money that movie would make with some cast given the confounders. Okay, that's called strong ignorability. And you've probably heard of randomized controlled trials. Randomized controlled trials are a way of enforcing strong ignorability, forcing what happens to be independent of what assigned causes were there. Okay? If I randomly give you Advil, then I have made these things independent. That's why RCTs are good for causal inference. Okay, but if you have observational data and you can measure W such that this is true, that's also good. So if strong ignorability holds, then you can estimate the causal effect with this iterated expectation. Okay, I take the expectation under the distribution of the confounders and the conditional expectation of the potential outcome given the assigned causes I care about and the confounder. And this is equal to the expectation I care about, how much money the movie would make with my weird cast that I made up. Okay, but as I said, famously, strong ignorability is an untestable assumption. In other words, I might measure a bunch of stuff about movies, but I cannot know if this is true. I might measure a bunch of stuff about genes or sports players or whatever, but I can't know whether or not I have measured enough stuff to be able to form predictions under intervention. So, how does this work? First, we want to fit a probabilistic factor model just to the assigned causes. Okay, and I promised a bit more detail about that. What I mean by a probabilistic factor model is a model that has this form, right? So there is an unobserved variable for each actor, beta j. There's an unobserved variable for each movie, zi. And then whether or not actor I is in movie j comes from a probability distribution that depends on the per movie variable and the per movie variable and the per actor variable. This little setup describes many, many models that you've heard of and probably use. Mixture models, matrix factorization models, deep generative models, topic models, et cetera, et cetera. These are all can be written down in this form. It might not be the form that you want to write it down in to compute with it, but it satisfies it is in this class of models. All right? Put a different way, open Chris Bishop's book to a random page, you're probably looking at a factor model. Okay, same with Kevin Murphy's book. Less so this book in the middle, but it's still a good book. All right, so many papers and books discuss probabilistic factor models. It's the world of unsupervised machine learning. In particular, all those things I showed you in the beginning, which was something like 10 years of research, those are all examples also of factor models. Okay, so this could find us confounders for doing fMRI analyses. This could find us confounders for doing population genetics. This could find us confounders for doing something about the causal effect of words in documents. This could find confounders about doing something about prices. Okay, and as a concrete example, Poisson factorization is one such model where I have a non-negative latent variable for each actor and non-negative latent variable for each movie, and then whether or not the actor is in the movie comes from a Poisson whose rate is the inner product of those two non-negative latent variables. Okay, and then just to be clear, what does it mean to fit this model? It means to assert that this is how the data arose, and then condition on who's in what movie and learn these latent representations, z and beta, from who's in the movie. All right, this is called Poisson factorization. It's kind of like a Bayesian version of non-negative matrix factorization. It can be fit to massive data sets with variational methods. I have a different talk about that. And it naturally handles sparse data like the movie data. Okay, but this is just one example of a probabilistic factor model. And you can see that its structure looks like I have a per movie variable zi, a per actor variable beta j, and whether or not actor I is in movie j comes from the interaction of those two. That's one point. The second point is I want to emphasize the revenue is not in this picture. We're just modeling who's in the movies. Okay? And so the hope is, and you can kind of see intuitively, that when you see all these movies, you'll be able to capture something like James Bondness just from the cast. I see that Sean Connery and whoever played M and Q and Miss Moneypenny are all together in these movies, and so that's going to get represented as one of the dimensions of this Z and beta. Okay, so that's the first step, is to fit probabilistic factor models to just the assigned causes. And then you want to check how well the model captures that distribution. Okay, and so I have extra slides at the end that tells you exactly how we do this check. But the point is, big numbers mean we're passing the check. Small numbers mean we're failing the check. We arbitrarily set the cutoff at 0.1. And the point is that these are 4 different probabilistic factor models, all fit to the same data, this movie data. And what we see is that 3 of them pass the check, and 1 of them, mixture models, doesn't pass the check. But I want to highlight for you that, remember, whether or not you've captured all the unobserved confounders is uncheckable. And this is a test. This is something I can check. Okay, so we use a predictive check on held out actors. We don't need to be able to compute things exactly. We just need to be able to form a predictive distribution that helps describe who's in the movie. And just to make it concrete again with James Bond, a model that when it sees M and Q in the movie predicts that Sean Connery and Miss Moneypenny are in the movie, that model is going to pass the check. It just doesn't work because I think it's because casts are heterogeneous. Yeah. And so mixtures makes a very hard assumption about that every movie just has one cluster. Whereas all of these 2 methods both allow movies to be heterogeneous, to have different types of actors in them. And this is a deep method, so it captures a complicated distribution of actors. Okay, so you've found the factor model, you fit it, you checked it, it passed the check. Then you use your fitted factor model to estimate the substitute confounders. And so what that means operationally is I take my fitted model, so I've got my betas in place, and my z's, and I calculate the posterior expectation of z. So this is z sub from Russia with Love. It's the expectation of its local variable given the cast of From Russia with Love and the per actor variables for the whole all of Hollywood. All right, and the idea is that these are the latent attributes of the movie that the factorization has discovered, for example, James Bondness, and we're going to use them as substitute confounders. You then form an augmented data set of triplets, who's in the movie, how much it made, and this mysterious z hat that comes from the model that you fit and checked. Finally, use the substitute confounders in a causal inference. For example, there are other examples, fit a regression from casts and confounders to revenue. All right, so fit this simple regression that takes who's in the movie and this substitute confounder and models the revenue that way. But this could be anything. It could be your favorite neural network. It could be logistic regression if you had a binary outcome. You don't have to use z-hat. You can use any function of z-hat. So something we use a lot is what we call the reconstructed causes, which is the expectation of A given z-hat. It can be anything like that. All right, and then the point of our paper is that if the factor model captures the distribution of the assigned causes, then you can use its local latent variable as a substitute for the multi-cause confounders. And again, there's a checking procedure in this. So you didn't have to think and worry about confounders explicitly. You had to do lots and lots of unsupervised machine learning on the actors, which you already knew how to do. All right, and that's how we get these pictures. Okay, so in the details part of this talk, for those of you familiar with graphical models, I want to give you kind of a theoretical intuition about why this works. All right, so I have just been asserting over and over again that this is a good idea, but I haven't really told you why it's a good idea. And here's the deal. Let's suppose you find a good factor model. In other words, let's suppose you find a factor model that captures the distribution of the assigned causes, the distribution of casts of movies. Then, given z, the local latent variable in that factor model, this conditional independence statement holds. The probability of who's in the movie, given z and the global latent variables, beta, are conditionally independent. Okay? Each person is independently, with a coin flip, added to the movie. Now, it's not an even coin. It's different from person to person, but it's independent. In other words, if I know it's a James Bond movie, then knowing that Miss Moneypenny is cast in the movie doesn't give me any more information about whether or not Sean Connery is cast in the movie because I already know it's a James Bond movie. Make sense? That's what that conditional independence statement says. Now, as a graphical model, it looks like this. Conditional on z, all of these a's are independent. And if you know graphical models, you know that you can read that statement off from that picture that I just drew. If I condition on z, it renders these a's independent. And this is for one movie. Now, the argument then goes that there cannot be an unobserved multi-cause confounder. Here is a multi-cause confounder U. All right, and what does that mean that it's a multi-cause confounder? It means that it affects how much money the movie makes, and it also affects multiple of these cast decisions, who's in the movie. And the point is that if such a variable existed that wasn't observed, then the independent statement that I just made could not hold. All right, and you can see that from this picture, because if you condition on Z in this picture, then there still is what's called a backdoor path, basically, between the casts and between the cast members. All right, the information can propagate from AI1 through U down to AIM, and so they can't be conditionally independent. All right, it's a graphical models argument. If one existed, the independent statement doesn't hold, therefore multi-cause confounders don't exist. And again, there could be a single cause confounder. Here's a single cause confounder that only affects whether Sean Connery's in the movie and the revenue of the movie. And this can exist because you can see, if you know about graphical models, you can see that conditioning on Z still renders these A's independent in this scenario. All right, so that's how we know that we can't rule out a single cause confounder. And this is untestable, I'll be clear. Okay. That's a theoretical sketch of why this algorithm works as promised. But in our paper, we've laid this out in more detail. Okay. Last part is an empirical study. We did a lot of stuff. Here are some tables and pictures from the paper we wrote about this that shows a lot of that stuff.
Sorry, so what you just said, how does it project to what you learned actually before on the strong
Good question. Honest question is what I just said, how does it relate to strong ignorability? So the idea is that strong ignorability is the assumption that I have observed all confounders. Enough confounders is a more precise statement. I've observed enough confounders to render who's in the movie independent of how much money that movie makes under every different cast. That includes multi-cause and single-cause confounders. The fact that there is only that we only need to have measured the single-cause confounders is a weaker assumption. Okay, so we did lots of stuff, and it's all in the paper. Well, let me show you one of the stuff we did. One of the things we did. We mentioned GWAS, genome-wide association studies. So this is a problem of multiple causal inference. How is genetic variation causally connected to a trait? In this setup, for each individual, or we're all individuals here, we have a trait that we measure, whether or not we can fly, and then many measurements of the genome, many SNPs. Okay, does that include questions? Okay, I'm almost done. Okay. So for each individual, we have a trait, whether or not we can fly, and then our genotype. Okay, so multiple cause confounding is a problem in this data set. Non-causal SNPs might be highly correlated to causal SNPs because of our ancestry. Right? I mentioned I'm Hungarian, and I'm a bad example in that like all my 4 grandparents are from the same small town in Hungary, and that has created a very specific genotype in my cells, and so some of the causal SNPs in that genotype are going to be correlated to some of the causal SNPs in that genotype are going to be correlated to the non-causal SNPs, and this will lead to misestimation of the connection between SNPs and the trait. Okay? So we are going to set that up in simulation to see how well the deconfounder works. We're going to generate SNPs. We're going to generate people on the computer where each individual belongs to some latent group. All right, so everybody's in some group, CI. We don't know that group, but we just assign them at random. And then we use the realistic model of SNPs from computational biology to create genotypes. So we now have our genotypes of whatever, 10,000 people. Then we set up the true outcome, this trait yi, which we're going to make a real valued trait. And yi is going to come from a regression model where there's some causal effect of each SNP, beta j, and then two terms, an intercept term that depends on the latent group, and an error term whose variance depends on the latent group, and this causes confounding, okay? Because y depends both on, the latent group helps drive both the SNPs you have and the outcome. And the intuition here is that the latent group is somehow, the intuition here is that there's some SNPs you didn't measure, and they are some causal SNPs, and so that's where this deconfounding stems from. That's where this confounding stems from. Moreover, many of these beta j's are 0. In other words, there's lots of non-causal SNPs, and we would get confused if we ran a simple regression. Okay, so let's just look at these two columns. So the columns here are different methods of fitting latent structure in this simulated genetic data, how well they passed the check, and then how well we were able to estimate the causal effects of each SNP in that scenario. Okay, we have access to the ground truth here because we're making up this data, and so we can measure how well we did. And what you see is we tried a bunch of different unsupervised learning methods on the genotype data, and again, many methods passed the test, and moreover, the methods that passed the test more accurately estimate the causal effects. The methods that didn't pass the test did not accurately measure the causal effects. And remember, in real data, you don't have access to this kind of information, but you do have access to this. If you naively, sorry, I should say what these numbers are. This is like just error, RMSE against the truth. And if you just did a naive regression, you're quite far away from the truth, so there really is a lot of confounding here. And if you magically knew the confounders, then you can do really well. Okay, but the point is here we do pretty well relative to knowing the confounders without knowing the confounders. Okay, so it turns out in GWAS, this procedure is done all the time. Okay, and it's not motivated through causal inference, but computational geneticists have, in many, many settings, looked at unsupervised learning of the SNP data followed by some kind of outcome model of the trait. And this justifies a lot of this work. In fact, this work was inspired by reading this paper, Song, How, and Story, 2015. It's a great paper. Okay. So to conclude, how do we understand the world through observation? This is important in many fields, and I showed you how to use probabilistic machine learning to help answer that question. We find, fit, and check a factor model, use it to form substitute confounders, and then use those substitute confounders in some predictive mechanism of the outcome we care about. This is checkable because I can check how well the unsupervised learning method captures the assigned causes, and it blends all of these ideas, model checking, unsupervised learning, and causality, and it requires weaker assumptions than the classical, pretty much untenable situation of causal inference from observational data. All right, I skipped many of the details, even though that might seem surprising, but they're all in this paper on the archive. If you're interested in some of the related ideas to this work, here's a bunch of references for good papers and books about unsupervised learning, about causality, about how to check models, about multiple causal inference, including Rajesh Ranganath, who's here at NYU. We've recently been applying this idea to make better recommendation systems, which is really a causal inference problem in some sense, that when you want to show somebody item, you want to know whether or not they're going to like it. That's an intervention. Thanks very much. Yeah. Yeah. That's a good question. The question is, can we do the same thing with time series? So it's a good point that underneath this was the assumption that the movies are all exchangeable. But if you had variables that are marching along in time, how could you work with this? So the answer is yes, and it's a research question. Like, yes, I believe you can do it. We have not worked out those details. You could work out those details too. It would be really interesting. I think that that's an important question. Yep. There was another question. Yeah.
I just had a question about the conditional independence of like there can be no multi-causal factors. My question is just like, is there more of a mathematical proof of that, or did I miss a statement because it didn't seem like evident? But you just stated that if we look at this graphical model, we can show that there isn't a second.
Yes, right. So graphical models are both kind of great intuitive pictures of structured factorized joint distributions and formal mathematical objects that reveal to us independencies and conditional independencies that are true in the joint distributions that they encode. And so there's an algorithm in graphical models, I don't know if you're familiar with it, it's the D-separation idea of understanding when two variables under a joint are independent or dependent. And it's through that idea that I asserted, but rested on this formal idea that indeed they are dependent. So it's a type of graph separation algorithm that tells you that. So it's not that there's nothing hidden under the rug there. It is a formal statement you can make about that graphical model that they are dependent. Yeah. Anna will be covering it later in her class. Yeah. I should have looked at the syllabus before preparing my talk. There was another question. Yeah.
How does the vector model-based approach compare with adding more interaction terms in the regression?
Great question. So, one question you might ask is, right, let's say I know some of the confounders, like action, like I know the genre of the movie. Should I add it? And the answer is we don't know. Basically, what we show in our paper is that you get unbiased causal estimates this way, but as for all estimation problems, there's an efficiency question, right? How much data do you need? And when you add these variables, then you lose, in some sense, statistical efficiency because you need more data then to estimate your causal effects. But there's a variance too, and you're lowering the variance of your estimator. And so, it's kind of case by case whether or not it will help or hurt. If it hurts, it's only because of the variance. So, if you have a lot of data, these aren't real questions. You could just do it. Add those variables because you have enough data to estimate the causal effects. Yeah. It certainly doesn't cause a problem outside of forcing you to need more data to estimate things. It doesn't add bias, in other words. But you want to be careful that you don't add a mediator. So in causal inference, there's two notions. There's these pretreatment variables and there's mediators, which are in between the causes and the effect. If you condition on a mediator, you mess everything up. I mean, not on purpose. Yeah, okay. It sounded more blamey than I wanted it to. If you add a mediator, there are problems with the downstream estimates. Yeah. Yeah.
Thank you for a great presentation. I have a question about the assumptions.
Yeah.
You talked about the strong ignorability.
Yeah.
But do we have to assume the stable unit treatment value?
Good question. So do we need to assume Sutva? We discuss it in our paper. I believe the answer is yes. Those kinds of, I see Sutva as kind of part of the poetry of going from prediction under intervention to like real causality. So it's almost philosophical. But yeah, we do, I believe, need Sutva here. I'm not positive. It would be in the paper. But I can be clear about the assumptions in the slide, just so that if you know about Sutva, then the slide is for you. So here are the assumptions. 1, there's no unobserved single cause confounder. Okay, so this is how we write that as a formal independent statement. 2, we assume overlap. Okay, and what that means is that conditional on the substitute confounder, the probability of seeing any cast given Z has to be bigger than 0 for all A. But let's be clear, if it's close to 0, then that's going to hurt efficiency again. right? Because you're going to need a lot of data to be able to do things, and you also you want to be careful that you're not extrapolating out of what your data is telling you. And that's also why we like to choose, all these factor models have some choice of latent dimension, k, and we like to choose k to be the smallest k that passes the predictive check for this reason. 3, we need the factor model to be identifiable, right? And that's not an issue with those books, Bishop and Murphy, but if you are adversarial, you can set up unidentifiable factor models and you'll hurt the estimation that way. It's not valid. But any Bayesian factor model will satisfy identifiability. Yep.
I think we have no more time for more questions, so let's take them offline. Let's thank the speaker again.
Oh, thank you. Oh, thanks, Anna. That's really nice. That's beautiful.
Participating in the seminar.
Oh, yeah.